Hi, I'm Bill Busby, and behind me here is Magic-1, my home-built mini-computer. If you're not familiar with Magic-1, it's a computer that I designed and built from scratch more than 20 years ago. And it's interesting in that it features its own special instruction set and CPU made out of mostly 74 series TTL logic chips. If you are familiar with Magic-1, then I should start with an apology. It's been a year since I've done my last video on Magic-1, and at that time I promised that I would be doing a 20-year anniversary video. And well, 20 years has come and gone and no video. See, there was something else that happened about that time, but we'll get into that in my next video. But this video is the result of a little side quest that I embarked on while trying to prepare for the 21st year video. And it was interesting to me, kind of interesting and nostalgic. And so I thought some other folks might be interested in it as well. So what happened was a month or two ago, one of my favorite channels, Curious Mark, had a segment on getting the old Altair BASIC interpreter running on a Altair 8800 computer using paper tape. Now, the Altair BASIC was Microsoft's first real product. It's kind of what launched the company. It was written by Bill Gates, Paul Allen, and Monte Davidson. And it is really quite interesting program in particular because it was able to fit a basic interpreter complete with floating point support into usefully running in 4K bytes of memory. And for myself, my start with computers really happened with personal computers anyway. Happened when I got my TRS-80 Model 1. And my first programming was done also in Microsoft BASIC, a slightly later version than the Altair BASIC. And my first, and then I moved into Z80 assembly language, which is sort of a superset of the 8080 assembly language that the original Altair BASIC was written in. So anyway, it seemed to me that it would be fun to get Altair BASIC running on Magic-1. Sort of a full circle of life thing there going on, where my first real memory of excitement about personal computers was when I first got my TRS-80 Model 1 and programmed in the little trivial, have it a program that asked you what your name was, and then it said hello, which to me was kind of amazing. Anyway, that's what this video is going to be about. I will spend most of the time, I think, talking about Altair BASIC. But let's start by showing you what I actually was able to do. In other words, I now have Altair BASIC, the 4K version, running on Magic-1. And if you telnet into Magic-1, you can try it out as well. So anyway, let me switch the cameras around, and we'll keep going from there. Okay, so this is a window into Magic-1, and let me go ahead and launch BASIC. Let's get that out of the way. And so we'll run BASIC. I hope you can read this. And in typical with those days, it asks for memory size, which basically gives you the opportunity to tell the basic interpreter to leave a portion of memory alone because you're going to do something with it. So this is setting up the limits, but we won't do that. And then terminal size is interesting because in those days, you probably would have been using a electromechanical teletype machine. And not a glass CRT. And so you'd want to tell it how many columns you could print with so you didn't end up running off the paper. But we'll just take the default, which is 72. And now it's asking us if we want some of the kind of more advanced math features, and we'll say yes. We'll go ahead and say we'll keep those. Okay, so what's kind of interesting about this BASIC is that it's a fairly limited BASIC. but it does have floating point. So if we go print 1 divided by 3, we get a nice 0.3. It also has the typical features you'd expect, for the minimal features you'd expect in BASIC. So let's do a little basic program here. On line 10, we'll print, and I've misspelled something already, and but that actually is a good segue into talking about misspelling. So if I were to hit the backspace key, it wouldn't do anything, because in those days, if you're dealing with a teletype machine, is a printing teletype machine, and so you can't easily backspace. And so we will use the underscore character to tell the interpreter to delete the last few characters. So print, so I need to delete 3 characters, and now we can continue print hello. And now if we list our program, it should show correctly at print hello, so we can run this, hello, and then you can do more advanced features. It has for loops and data reads, input, subroutine calls. So let's just do a quick one here for I equals 0 to 5. And we'll go line 20, print I, line 30, next I, and we'll go do a subroutine. Whoops, I misspelled again, so I've got to do the underscore trick. So we'll wipe out those 2 characters, add a space, and go sub 100, line 50, let's go ahead and stop. We'll say end. Then at line 100, we'll print I'm in a subroutine. And 1110, return. So let's list that. And we should just do a little bit of printing here, so we'll go ahead and run that. And it works. It also supports arrays and comments in programs, and not a lot else. But again, the key feature there is that it works in 4 kilobytes of memory, which is not a lot, and it supports floating point. So let's go ahead and exit. We'll go by, and now we're out. Okay, so what I want to talk about in the rest of this video, what made this kind of an interesting little side quest is that I found it very nostalgic. You know, I got my start with computers with TRS-80 Model 1, which ran a later version of Microsoft's BASIC interpreter, and my very earliest programming was done in Microsoft BASIC. And more than that, though, to get this working on Magic-1, I had to translate the program from using the 8080 CPU to Magic-1 CPU, and that got me kind of deeply involved with some of the crazy programming tricks that had to happen in order to make it all work in such a small amount of memory. And so most of this presentation is going to be talking about those little tricks and how they were used, and these were commonly used tricks back in those days. And then I'll get a little bit into how I managed to get this working on Magic-1, and at the end, it did leave me with some suggestions about some weaknesses in Magic-1's instruction set that I may or may not, we'll see, end up changing the microcode. I haven't changed the microcode since 2007, but this did introduce some good candidates for new instructions. Okay, so let's so I can keep my things straight here. I've got a little slide set, so let's switch over to that. And let's get on with the presentation here. Okay, so I do want to also give some acknowledgments here. It was super useful to me in this process. There's a website called altair.basic.org, and Ruben Harris and Charles Mangan did a nice commented disassembly of the Altair 4K BASIC, and that was extremely useful in getting this thing to work. Now, as it turns out, after I completed this, Bill Gates actually released a huge listing of the original source code with comments of Altair BASIC, and not just the 4K, but the 8K and 12K versions. And I just kind of flipped through that. It would have been a whole lot easier if I'd had that when I started this process, but I didn't. And what was there on AltairBasic.org was incredibly useful. And then also critical was the Altair simulator that Peter Shorn put together on top of SimH. And that enabled me to have a comparison of what Magic-1 was doing versus what the Altair would have done. And together, that made this process really possible. I don't think I would have stayed with it if I didn't have that to help me guide me. Okay, and so I've mentioned it briefly. What we're going to talk about in this presentation, we'll talk a little bit about the differences in the Magic-1 and 88 instruction sets, the programming tricks that needed to happen to make it all work, some of the challenges I faced, how I actually did the translation, and then we'll finish up with some tweaks that I may or may not make to Magic-1's instruction set. Okay, so back to the beginning. So the Altair 4K basic interpreter, it was written by Bill Gates, Paul Allen, and Monte Davidoff, and that's the name I forgot. I apologize for that. And it was the first product of what became the Microsoft juggernaut. It was typically sold on paper tape, punched paper tape, for $150 for the Altair 8800, and that was fairly expensive. As I said before, supports for loop, goto, go sub, standard arithmetic, and so on. But really the part that I want to spend some time on, and I think the part that's most important, is that it ran in 4 kilobytes of memory. 4K of memory is not a lot. And to have full floating point support and room for the interpreter and room for the program is kind of an amazing thing. And so let's talk about how they were able to get that all to work in such a limited environment. Okay, so when people look at Altair BASIC, they're kind of struck, I think, by some of the tricks that were used, the programming tricks. Now, I want to be clear, this is not a criticism at all of Bill Gates and company when they wrote this. These are the tricks that you had to do back then in order to work around the limitations of such a small memory footprint. But these tricks, if you try to do them today, would probably would get you fired, and it should, because they're really awful. But I like to think of these things along the lines of being necessary evil. They are really kind of bad things to do, but doing them enabled this to happen. And so it was really, you just had to do that. So let's kind of go through some of these tricks. Now, the first thing that I want to mention is that once the Altair BASIC interpreter was loaded into memory, there were only 260 bytes left in storage for your program and the variables. And, well, you could not do a lot with 260 bytes. But the first big, nice trick that they did is when you start up the program, like most programs, you have an initialization phase. Where you're setting up variable values, you're building tables, you're initializing your I/O devices, but that only needs to happen once. It needs to happen once at startup. And so what they do here is they've basically put all that initialization code at the end of the image. And so if you start kind of at address 0, it disables the interrupts and then jumps to the initialization routine, which does all the initializations. And then after it's over, it will rewrite that initial branch to jump to the main program. And effectively, it frees up that initialization memory that was only going to be used once anyway for data. And then Also, some of the more expensive floating point operations, sine, random number generation, and square root, might not have been used by everybody. So they put that code at the end too, and that was that question at the beginning saying, do you want sine? And so if you weren't going to be using those functions, then you could say no and eliminate them. And in the end, you'll end up between 727 and 973 bytes free. And that's enough to do some stuff with. So that was trick number one, which was pretty standard. There's nothing particularly evil about that. That was sort of a benign trick. But we're going to move into kind of progressively nastier things. So the next little trick that was used, and this is something, again, that is completely benign. It was a kind of typical way. In fact, even as I remember some of my old college textbooks described this as a legitimate mechanism for passing arguments to a function. So let's just take an example here. If you had a procedure call where you wanted to do a syntax check to see if the next character is what was expected, what you would typically do today is you would, load up the character, you would push it onto the stack or store it in the frame, and then you'd call your syntax check procedure, which would then load it out of the frame and go on. But if we look at that, just the straightforward way of doing this would require 7 bytes for every syntax check. But now, if we use the inline argument passing, we can actually reduce that to 2 bytes, go from 7 to 2 bytes. And this is kind of cute. The 8080 and the Z80 have a special compact function call instruction called restart. And there's just a limited number. I think there's, off the top of my head, maybe 4 or 6 or 8. I don't remember quite right. Special locations where you can basically do a subroutine calls. The same thing as a call, except it only requires 1 byte of instruction to do the call. And so for these common functions, Altair BASIC would use the restart to enable you to get by with just calling, with just 1 byte instead of 3. But the next thing that follows is what's kind of interesting. And so if we look here at, let's see, down here, restart 1 means do a subroutine call to address 8. And then it's followed by define byte, which is just the data, a single byte of data that's actually embedded in the code immediately after the restart subroutine call. Now, what will happen now is that the restart instruction will push the return address on the stack like subroutine calls do. And in this case, though, that return address is going to be pointed to the define byte, the argument. And so if we look at what happens once we get into the subroutine check, it will basically load. Here, I'll go back to. So here we're loading the byte of the basic program to check with, exchanging the value on top of stack, which is the pointer to the inline argument, and now it compared with HL. So HL and top of stack get exchanged. Then it compares the next byte of the program with the argument byte. And now it's going to increment the return address because it was pointed at the data. And so now we're going to point it past the data so execution can resume. And then it exchanges it back. So it pushes the updated return address on the stack so that eventually when the program wants to return from the restart of the call, it goes to the right place. And this is a situation, this is a style of argument passing that really works best when you're passing literals. But it is kind of slick, and it's an extremely compact way of doing calls. And so if you have in the program, like syntax check is fairly common, and they're saving 5 bytes at every call site, which is pretty good. Okay, now the next trick is self-modifying code. Now we briefly mentioned self-modifying code in the first part where I talked about how after startup the program would jump to the initialization code and then rewrite the original branch at the beginning of the program so that it would no longer try to branch to the startup code once you reset the machine. And that's effectively, you can think of that as a warm start versus cold start. So the cold start, when you first turn on the machine or first reset after loading the program, it would do the initialization, then wipe out the initialization code, rewrite the branch so that a subsequent reset would skip the initialization, which you can't do anymore because the code's gone, and just land you back into the main part of the program. Now, that was just one of the uses of self-modifying code, and this is actually a pretty common technique, particularly in early computers. So you could, again, you could save memory, like the example I just gave. I have here overcoming limitations in instruction set. I don't remember which instruction set it was, but I do recall there was an instruction set I was dealing with that had a shift operator where the number of positions to shift was embedded in the instruction. They didn't have a variable shift. You could either shift by 1 or 2 or 3 or 4 and so on. And so the way you would do that is if you had to do a variable shift, you would actually create the proper opcode in the shift routine and then store it and immediately execute it to shift the right number of times. And then another common thing that actually Altair BASIC and later on Windows used extensively was customized specialized routines, helper routines. The example in Windows that was typical was bit blitting, and this is where if you're going to, well, actually, I'll get into that a little bit later. But I do want to say that today this is considered a very bad thing. You don't want to allow self-modifying code. It's just an open invitation for virus insertion. It's very difficult to debug, and actually, personally, in my career, most of my career dealt with dynamic translation systems and JIT compilers. And like at Hewlett-Packard, I did the system that ran PA RISC code on Itanium systems, and it did this by translating on the fly the PA RISC code into Itanium code. And then at Transmeta, another company, that it translated x86 instructions into an underlying VLIW architecture. And then even at Google Android, when I did the Dalvik JIT compiler with Ben Chang, it translated the bytecode into ARM code on the fly. And that self-modifying code prevents a serious problem there, in that if you're translating code as it's running, if the code changes itself, it invalidates the translations. Now, at HP and at Google, that turned out not to be a big problem, but it was a serious problem at Transmeta because Windows did this extensively, particularly with bit blitting code that basically wrote little glyphs and things into the frame buffer for display memory. You could easily write a generic routine that would patch overlay a set of bits into the frame memory, but you needed it to be fast. And so the way it was typically done is if you wanted to do a bit blit, you would call the bit blit generator, which would say, do I have an existing piece of code that does exactly what I want to do? And if not, it would take a template and create that. And then we would execute it directly and not have to interpret. Anyway, I'm getting kind of off track, but it was considered a bad thing, but it's also really useful in some situations, and it's used here in Altair BASIC to speed up some of the floating point manipulation. Okay, so anyway, let's go ahead and go through some of the examples. So I've already talked about this one. This is the cold start, warm start, so we can just skip past that. It just basically the code rewrites that initial branch so that we don't have to do so we can free up the initialization code. The next one, it's port configuration, and so this one's kind of interesting because it was targeted for the Altair, and you could have third parties created cards for the Altair with different types of I/O ports, and they might live in different places. It might, your serial port might be port 5 on one machine and port 9 on another. And so the Altair BASIC had a piece of port configuration code that would go and write in the proper port numbers for the I/O routines based on what card you had. It wasn't smart enough to go identify which card you had. You kind of had to tell it. But that was another bit of self-modifying code. Instead of having, like if you wanted to, like in this case, read the status register, instead of having the code ask, okay, which port should I read, it just patches the input instruction to give it the correct port number. Okay. Now, this is probably the more interesting one, the custom helper functions. This is kind of like the bitlit routines. And an example here is the floating point multiplication, where you've got kind of a generic inner multiplication loop here that is going to be loading up a piece of one of the operands. And it starts off as a template where it loads HL register pair with all zeros. But prior to falling into that loop, the multiplication routine here will actually store and patch up the inner loop helper to have the value that you want to have, that you're going to kind of repeatedly loop around and do an addition to. And this kind of thing can significantly speed up processing, and it was continued to be done even in later BASICs. So I took a look at the TRS-80, Microsoft's BASIC that went into TRS-80 Model 1, and it also had some helper routines that, even though, so I should have mentioned this before, most of the BASICs that people would have been familiar with that went with the TRS-80 and the various other micros of the day existed in ROM. And so you cannot do self-modifying code in ROM, but in those cases, part of the initialization code for the BASIC was that they would copy sections of code that were to be modified into RAM, and then they would patch the RAM versions. And so that's how they were able to do self-modifying code in a ROM-based BASIC. They just copy the right bits out first. Okay, and now let's get to probably the nastiest of the little programming tricks. And this one is effective. It certainly saves space, but it's pretty ugly. So it's jumping essentially into the middle of an instruction. Let me just explain. Let's take this example here. So this is an actual example from the Altair BASIC, and it deals with setting up the error code for various errors. Now, if I were to write it in C, it would be something like this earlier on. If you were out of memory, then you'd set your error code to 12. Else, if it was a syntax error, set the error code to 2. Else, if it was divide by 0, set the error code to 20. Now, if you were to translate this section of code into assembly, there'd actually be quite a few instructions. You have a comparison, and if it didn't match, then you jump to the next section for the next comparison. If that didn't match, you jump to the next section, but if it did match, you would then set up your error code. But then you would have to do another branch to branch out to the common point. And so this would actually expand into quite a few instructions. But the trick that was done here is that if we look here, so here's the out of memory where we're loading a 12 into register E. And following that is just a byte of one. And if you look at that, what's going on there. This is not an instruction. Typically, this is actually a byte. Well, what actually it is, one is the opcode byte for an LXI of the BC register pair to give a 16-bit value. So an LXI BC or B would load this value, 021E, into the BC register pair. So if we enter out of memory, we load E, then we hit this 1, which the machine interprets as an LXI. And so it will then look at the next 2 bytes of memory, this 1E02, and it will load that up into the register pair BC. Now it will fall into another 1, which is another LXI, and it will load up the next 2 bytes with 1E14. Now, we don't actually care what is loaded into BC. That's just junk. But what effectively is done is if we enter here, we get a 12 into E. But if we enter here, we move a 2 into E, and then hit the DB to kind of skip over the next 2 bytes. So this is essentially a skip sequence. So depending on where you enter, it's going to put a different value in register E, and there's no need to have branches to rejoin the common code that starts here with error. And there are, in this example, they use the LXI opcode, but scattered throughout the code are other kind of situations like this where you only want to skip 1 byte. And so they have a different opcode. In another place, there's a branch, a conditional branch that they know will never be taken, but it will effectively swallow up the next 2 bytes. So you can avoid having to, in this case, you can avoid having to move 12 into register E and then jump to error, which would be a 2 or 3 byte sequence. And so this saves a lot of space, but man, it's pretty ugly when you're trying to figure out what's going on there. Although, interestingly, I should say that this technique was effectively legitimized by following architectures like the ARM architecture, and even PA RISC had instructions that had, as part of the instruction, conditional skips. And so if you did an operation, depending on the condition, it might skip or nullify the following instruction. And so at HP, when I was doing PA RISC code, there was quite a few times where I did this kind of sequence, but it wasn't using kind of incomplete opcodes. It was using conditional skips, which made it, I think, a little bit more legitimate. But that's in my opinion, that's kind of the nastiest of the little tricks that were used. Okay, so that's just a little overview of some of the things that were going on with Altair BASIC. But let's talk about how I got this working on Magic-1. Now, obviously, it won't just directly run on Magic-1. Magic-1, excuse me, has its own processor where Altair BASIC was written in 8080 instruction set. And I had some choices when I thought about how am I going to do this. One thing I thought of, well, I could just write an 8080 simulator running on Magic-1 that would simulate the 8080. That would go pretty slow, and it felt kind of indirect to me. The next thing, I thought I would just take the 8080 instructions and just do a direct translation to Magic-1. And I actually started going down that road, but once I started getting into the floating point code, I decided that was going to be too difficult. The floating point code is clever and dense and a little bit, I'd have to understand it a lot better than I was really interested in doing. And so what I ended up with is kind of what we call a template translation system. I just wrote a little program using Lexignac that would read the source code for Altair BASIC, and for each individual instruction, it would translate that instruction into a sequence of instructions using Magic-1 instruction set. And it still required some adjustments. It wasn't like I could just run it through and everything would work perfectly. But it worked, and that's basically how I did it. But to talk about that a little bit more, let's kind of briefly go over the differences in the instruction sets between the 8080 and Magic-1. The most striking difference are, of course, the registers. Now, the 8080 is fundamentally an 8-bit machine, and it has a number of 8-bit registers, A, B, C, D, E, H, L, and the B, C, D, E, and H, L can also sometimes be used as a register pair, the two of them together. On Magic-1, I also have A, B, C, but these are strict 16-bit registers. So there isn't a 8-bit version of these registers. However, Magic-1 does have 8 and 16-bit operations. So I can load 18 bits. I can load 8 bits, store 8 bits, do an 8-bit add that only looks at the least significant portion of the register. But I don't have the ability to do something with the upper half of a register. So it's either 16 bits or the low 8 bits of the register. Another difference that was a little bit challenging is that the 8080 has a unified 64 kbyte address space. And so code and data, it's all the same. There's whether at address 27, it might be an instruction, it might be data. If you're loading from address 27, you're getting whatever's there at address 27. Magic-1, however, has split domains between code and data. So it's got 64 kbytes for each process, for each individual process, can see 64 kbytes of code and 64 kbytes of data. And in general, you can't have code loaded as data. It's a strict separation. Now, I'll talk about the ways you can get around that, but let's move on. The other big issue is that the 8080 is a little Indian machine, and Magic-1 is a big Indian machine. And what that means is if you've got a 16-bit number that you're storing into memory, on the 8080, the least significant bit comes first, and then the most significant bit follows. Most significant byte follows. Whereas Magic-1, the most significant byte comes first, and then the least significant byte follows. Now, I'd imagine this was going to be a bigger problem than it turned out to be. Because if you're only dealing with byte operations, then Indian doesn't matter. It really only comes into play when you're dealing with things that are stored in memory as 16 bits. And it did cause me some problems, but it was fairly easy to work around. Okay, so let's move on here. On the instruction set, there's a lot of text here. I'm not going to go into it too much, but again, the 8080 largely does 8-bit instructions, 8-bit operations. Magic-1 can either do 8 or 16, but there is one big nasty difference. Well, actually, a couple big differences. So on the 8080, you have a fairly rich set of rotate instructions. You can rotate left, rotate right, through the carry or not through the carry. Magic-1, I didn't see the need to do much in the way of rotates. So we don't have any rotate instructions. We just have shifts. We can shift left, shift right, and it doesn't involve the carry. And so that turned out to be a significant difference. The other nastier difference is that the sense of the carry bit is different on the two machines. So for additions, the sense of the carry bit is the same between Magic-1 and the 8080, but for subtractions and comparison, the sense of the bit is flipped, and that did actually cause a fair number of problems we can talk about here in a second. Okay, so now I guess now we're here, the condition codes. In addition to the sense of the carry being different, the instructions that alter condition codes were also different. Now, so for example, on the 8080, all the logical operations, and, or, XOR, whatever, cleared the carry bit. On Magic-1, they don't. I'm not even sure that there's a particular global statement I can say about the carry bit on Magic-1. When I designed it, I really didn't put much thought into what the carry should be after a logical operation. And similarly, there are some operations in 8080 that will only set the carry bit but leave the rest of the bits alone, and they don't match up well with Magic-1. And so that became an issue if I'm trying to have a code sequence for Magic-1 that exactly does what the 8080 instruction does. I have to do the instruction, but I also have to make sure that the condition flags end up being the same. And kind of compounding that problem is that Magic-1's instruction set does not easily give me the opportunity to directly manipulate condition flags. So, for example, I can move the condition flags into a register and operate on them, but to basically store them back to the status word, I can only do it by pushing on the stack and popping into the MSW, the machine status word, and that is kind of ugly. Okay, now the other I'd mentioned before that the 8080 can deal with treat a register as 8 bits, but then a register pair, whereas Magic-1 can only deal with either the lower half of the 16-bit register or the full 16-bit register. And that became a bit of a problem. But the way I tended to work around that is that I defined the emulated 8080 registers as a memory structure. And so I'm not trying to directly map, say, register A in the 8080 to register A on Magic-1. I've got them stored in memory, and that worked well, but it does make things a lot slower. So I think I'm about 1/6 the speed of a 2 megahertz 8080 when I'm running the Altair BASIC on Magic-1, which doesn't bother me because it's to me, the interesting thing was getting it running, and even at 1/6 the speed, it still functions. You can still do little basic programs that look fine. Okay, the other one I've mentioned before, Little Indian versus Big Indian. In general, it didn't matter that much. I did decide to go ahead and allow, when I'm doing pushes and pops, I just retain Magic-1's native Big Indian form. And so long, if you push and pop, it doesn't really matter whether they're stored Big Indian or Little Indian on the stack, as long as you're consistent. Though there was a place in the code where it operated directly on things that were stored in the stack, and I kind of had to rewrite those to get it to work. But by and large, it wasn't a problem. Although I did end up having to make some enhancements to Magic-1's assembler and linker to support initialized addresses that were initialized in Little Indian format instead of Big Indian. But again, that wasn't that big a deal. The last issue was really more of you almost considered a bug in Magic-1. Magic-1 needs the stack pointer to be aligned, 16-bit aligned or 2-byte aligned, and this has to do with page faults. There's nothing in Magic-1 architecture which prevents you from having a stack pointer that's at an odd address, but there's an issue with page faults, and there's at least one instruction that if you're pushing a 16-bit value onto the stack where one of the bytes is on a page that's present, but the other byte is on a page that is not present and triggers a page fault, that you can end up with the stack pointer being corrupted. And I'd forgotten about this because I have the software convention of always keeping it aligned, but I actually did run into this problem because there are places where Altair BASIC doesn't care whether the stack is aligned 2 bytes or not. and this did trigger, and I just did the my workaround was a bit hacky, but it was good enough to get it running. So at startup of Altair BASIC, before I get into the real code, there's a little routine that will actually write to read and write from every data page to force all the page faults to happen up front, so that then there are no subsequent page faults, and so we can go ahead and have a misaligned stack. And again, this is something I might fix in the future if I ever end up doing a change to the microcode. This is something I can probably deal with at that time. The self-modifying code, again, it didn't turn out to be much of a problem. I did have to do a little bit of rewriting, but it's fairly easily dealt with. Because in my translation, I didn't have to worry about the saving every byte of space. I could use the longer form versions that avoided the self-modifying code. And so again, it really wasn't much of a problem. And I should say that I'd mentioned earlier the inline argument passing. When I designed Magic-1, it did occur to me that there might be a situation in the future where I wanted to be able to load data from code space. And I added an instruction that will do just that, load code.8 a indirect b. And I'm kind of tickled because this is really the first time I've ever been able to use this. So I was able to use this to handle the inline argument passing, so I can go ahead and completely do the old Altair thing with the inline arguments. And I'm actually was pretty happy about that, because I thought I might need that 20 some odd years ago, and now 20 some odd years later, I now have a use for that instruction, and it actually worked just fine. Okay, so just this has been going on too long, so I'll try to zip through the rest of this. But the translator itself, I used Lex and Yak, or more specifically Flex and Bison, which are the GNU names. And those are pretty useful tools I've found for just knocking out quick and dirty translators. I relied on the Altair simulator to do debugging, and again, that was an enormous help. And then to assist in debugging, I actually modified my my cheapo debugger that I have on Magic-1 so that it would output machine state in the same form that the Altair simulator did, to make it easier to compare. So I would get traces from my program through the debugger and traces from the Altair simulator, and then I could compare them. And that made life a lot easier. Okay, so let's wrap this up. My voice is going away. This process has made me think that maybe I should do another round of changes on the instruction set. And the ones that would have been most useful to have, number one is a carry complement instruction, just an instruction that complements the carry. The 8080 has that. A lot of machines have that. And if I had that one single instruction, then my Altair BASIC running on Magic-1 would go faster by about 20%. So roughly 20% of the execution time is messing with the carry to flip the sense of it, because the sense of the carry is different between Magic-1 and the 8080. Also, to make it easier to manipulate the directly manipulate the condition flags, having a instruction, Magic-1 actually does have an instruction which copies register A to the machine status word, but it's only accessible in supervisor mode. And my intention there was that you use that instruction to enable virtual memory and to enable interrupts and stuff, like that you wouldn't want a normal program to do. But I could fairly easily change that so that You could still do it in regular user mode, but it would only affect the condition flags and not affect the program control flags or machine status flags and machine control flags. Another instruction which would have been useful to have, super useful, would be a byte swap, to swap the high and low bytes of a register. And I've actually run into this before on Magic-1. It would have been a nice to have. Then similarly, the 8080 makes extensive use of register exchange instructions, and those can be actually quite useful. And I never had a use for them because when I did Magic-1's instruction set, I was largely thinking of instructions that would be useful for the C compiler. But when doing assembly language programming, being able to swap registers is a pretty useful thing. And so a few register swap instructions would be good. And then finally, at one point I actually had this in the instruction set, but I removed it for something else, and that's to clear the high byte of a register. Now, Magic-1 does have, excuse me, a sign extension instruction, which will do a sign extension of an 8-bit value into 16 bits. But this would be something that would just clear the upper byte of a 16-bit register. And that is something that would be useful in general. In fact, even the compiler could make use of that when it's dealing with unsigned 8-bit operations. Okay, anyway, so I think that's it. My voice is kind of cracking here, and this has gone on again way too long. But I will say I do promise that very soon I'll come up with that 21st anniversary of 21 years of Magic-1 operation, and there's also something special that I'll be talking about then that if you like Magic-1 you may find quite interesting. Anyway, sign off for now, and thank you much.